the exhibits later this afternoon, that kind of stuff.
Okay, welcome everyone to the Educational Programs Live Q&A panel at the 2021 CubeSat Developers Workshop. We are excited to have our panelists and attendees join us for an engaging discussion about their presentations. So first, I want to remind everybody that there's still a lot of interesting exhibits going on this afternoon, so please be sure to check them out and take some time to take a look at all the cool stuff going on. So now I would like to introduce our moderator for the Educational Programs Live Q&A panel, Ben Malphrus. So I'll kick it over to Ben and he can tell you about himself and our panelists.
Fantastic. Thank you, David. Well, welcome everyone to the education panel, and fantastic talks today. I really enjoyed watching them. Have to admit, I actually watched a couple of them at least twice, so I really kind of appreciated the recordings. But let me go around and briefly introduce the panelists, and then I'll have you guys each give a little bit more in-depth introduction. And then I'm going to take the liberty of asking the first question after the introductions. That's one of the rights as a moderator that I appreciate. So the first panelist is Bjarke Gotfredsen, who I could say a lot about Bjarke, but the first thing that comes to mind is an old friend of mine and collaborator. And Bjarke's talk on the XinaBox today and the modular technology surrounding it, I think was very fascinating. So let me have Bjarke say a few words about his affiliation and himself, and then we'll move on to the next panelist. Bjarke?
Oh, thank you, Ben. And nice to see you again. Yes, so XinaBox, you've seen the video, I hope. So you know that it's a modular technology that allows you to put together at least something that assembles to a satellite or a satellite-looking technology, so you can use it in education. We developed this thing here now 5 years ago, and the first launched with the ThinSat program that flew from Virginia. And we actually used the technology before that from Ben Malphrus's alma mater from Morehead State University here in South Africa. And we decided to kind of like upgrade it a bit, and therefore had an opportunity to reciprocate with that technology. So yeah, I'm the founder, inventor, and the head of XinaBox, and very, very happy to be here. Thank you, Ben.
Thank you, Bjarke. We appreciate your being here. Next, we have Rebecca Keenan from MIT, and there's an interesting collaboration between MIT and Lincoln Labs, and I imagine Haystack, I assume, has some role. But building a CubeSat with students in 4 weeks in a organization called Beaverworks. And Rebecca, could you tell us a little bit more about yourself, please, and the program?
Hi, so my day job is as a research engineer at MIT Lincoln Laboratory, building prototypes of small satellites, primarily. I've also done a lot of RF SATCOM. And the Beaverworks Summer Institute is a collaboration between MIT campus and MIT Lincoln Laboratory. The BWSI, or Beaverworks Summer Institute, is a 4-week-long world-class rigorous STEM program for rising high school seniors. It's a full-time a free of charge program that focuses on project-based learning in engineering. All of the courses are taught by engineers or scientists who are working either at Lincoln Lab, on campus, or at other organizations in the Boston area, like MITRE, for example. I teach the Build a CubeSat course over the summer, as well as a variety of Build a CubeSat outreach programs that we've added on more recently. In that program, we have the students work in teams to build their own prototype 1U CubeSat. And then we partner with Woods Hole Oceanographic Institution to get a ocean science imaging mission. We use a Raspberry Pi camera to have the students demonstrate that mission in our final project.
Fantastic. Rebecca, thank you very much for joining us. And I want to talk about the zipline mechanism that you showed in your talk a little bit here in a second. I found that fascinating. Next, we have Daniel Lee, who's a high school physics and engineering teacher from New Jersey, who gave a fascinating talk on ThinSats, PicoSats, and the NGSS curriculum. So Daniel, welcome. And could you give us a quick overview, please?
Yeah, sure. So I always feel like an outsider at things like this. So I'm a high school teacher. I'm currently in my classroom right now. I have a student working on actually a ThinSat right now. But basically the whole basis of the curriculum kind of comes from this idea of, rather than trying to fit things into a single academic year, instead, what I've kind of been trying to manipulate is this idea that I have these students for a total of 4 years. So kind of taking the similar approach to how a university might do it with their students, and be able to kind of look at this as an independent project almost that spans the entirety of those 4 years, and be able to really integrate and get to a high level of the integration between science and the engineering resources. So, you know, instead of separating kind of the engineering and the science, students can really see the cohesiveness in that. So obviously, thank you for having me here. You know, it's a huge honor, and hopefully I can answer some questions that will be helpful.
Fantastic, Daniel. We appreciate your efforts toward the building the pipeline into universities and then into the aerospace community. It's essential. Fantastic. And last but not least, we have Pauline Faure, who works where it all started, at the Cal Poly CubeSat laboratory, and fascinating talk on the PolySat program there and how students are involved. So Pauline, would you please give us a brief overview?
Yes, thank you, Ben, for the introduction. So my second job, well, but I'm not sure which one is the first and the one is the second one, but I'm also a professor in the aerospace engineering department. And so the idea that Cal Poly CubeSat kit, though a kit by itself is not a novel idea, was really stemmed from the learn by doing aspect of Cal Poly that the CubeSat laboratory has been embracing, and having that opportunity for my 70+ students to potentially touch a satellite prior to graduating, and not necessarily limit that to the people that goes to the laboratory, but also expand that to that community of the university, and then expand that to even newcomers. Like we had a project going on with Cambodia where we're thinking on reusing that for them to have that as actually as the first satellite for their country, and also apply that to different professional training we have been going on with the CubeSat laboratory.
Fantastic. Thank you, Pauline. We look forward to hearing more. Let me point out to the audience that in the chat room, you can see links to the pre-recorded presentations. If you haven't had an opportunity to view those, I highly recommend viewing these 4 talks. They were absolutely fascinating. And please, if you have a question, enter it in the chat box, and I'll ask the panelists. But if you have a specific panelist that you would like to address the question to, please also include that in the chat room. So I'm going to mix it up a little bit and sort of throw out some random questions here. I'm going to start with Rebecca. Gosh, the Beaverworks Build a CubeSat. It's a fascinating program, incredible program. and you have these young engineers for 4 weeks, and you take them through from where you begin to where they end with a functional CubeSat system is, to me, pretty extraordinary in 4 weeks. So my first question is to take them from sort of a novice level of expertise to where they're doing integration and testing and actually taking data in 4 weeks. What level of expertise do they come in with? Do they come in with knowledge of basic electronics or some programming, or do you have criteria for selection, or where do they start, I guess is my question.
That's a great question. We were actually just doing admissions to the program this week for the summer program. So we're right in the midst of what are the criteria for students coming in. The Beaverworks Summer Institute program really starts in January and February with an application process. We have an online course using the Open edX MIT platform that the students all have to complete. So for the Build a CubeSat course, we have some CubeSat specific material that covers the basics of like, what is a CubeSat, a little bit about orbital dynamics where they actually use SDK. We talk about the space environment, outgassing, and radiation. They also complete some basic things on circuits, and because we use Raspberry Pis as the flight computer, we also have a module on using Linux and the Raspberry Pi, so that everyone comes in with a little bit of a foundation. And then we also have a Python core course. The nice thing about this course, it was actually developed by one of the other course instructors, and we have another course called a Cognitive Assistant or CogWorks course. And he developed a Python class on edX that the students take. It's actually open to anyone on pythonlikeyoumeanit.com. You can see all of the material. It's a great Python course. So the students come in with a very diverse background. Some of them have taken AP Computer Science and they're in FIRST Robotics and they've done a ton, and some of them have very little experience. But the edX course gives them all a chance to get some basic background knowledge and for us to be able to evaluate, are they motivated? Do they have the ability to kind of pick up this information quickly? So we kind of assume they've got a little bit of programming, they understand some basics, and then coming into the first week of the course, we really just hit the ground running with talking about systems engineering and how to think like an engineer. And that really helps to start like that. We also have them start using hardware from day one. We start working with the hardware right away, which I have found helps a ton with just breaking that initial hesitancy that a lot of students have with working with hardware. So our first project, which we call the FlatSat Challenge, we give them a lot more help for that project than they get in future projects. So they get that initial sense of feeling successful right off the bat, and they finish that project within the first couple of days of the course. We also have the advantage, is very different than a traditional high school class where we have them full time. So I have about 6 hours of instruction with the students every day. And then they'll often work after class. I don't assign homework, but these students are extremely motivated. And so they will sometimes be working until pretty late at night, even if I've told them they don't need to. So we go through material really fast. Week 2, we cover all of the basic subsystems that they have. And then in week 3, they start applying that to their own system. We have a lot of reviews with them, a lot of times with myself, the other instructors, and our TAs are meeting with teams directly to help them work through things and understand. One of the other benefits that we have is having a very large team. So I have usually 3 TAs, which is a lot for a class of 25 students. And then I have a team of a lot of instructors who come in and give guest lectures here and there who are experts in their field. So we're really exposing these students to a lot of help, which kind of increases the pace, and they're working together in groups where they can kind of learn collectively. So by the end, they are doing link budgets, they're doing power budgets, they're doing ConOps, they're understanding mission operations, they are taking pictures and doing image processing on those and downlinking them to their ground station. And then they're having to present to me the results and what they learned from that and how they would apply that to a future real flight-worthy system. So I really think they get a lot by the end of it. It's really great to see every year how far the students come in such a short amount of time.
Absolutely. It almost seems like the content of an entire undergraduate engineering systems engineering course compressed into 4 weeks for these kids. So that's extraordinary. Yeah. I'm going to break my protocol and ask Rebecca one more question that came up here, just because I think it's very timely. Harmon Karud would like to know, how can he sign up for this course? And actually, I'd like to know that too.
Yeah, so unfortunately, the course sign up for this year is already passed. We actually will be sending out our final admissions decisions in just a couple of days. But we have a fall program that we're starting this year with, there's a couple of organizations that we're working with to try to provide opportunities to more students. So this will be a more self-paced kind of thing. And the applications for those, I think, will be out mid-summer. And then usually the applications, you want to get going on them in kind of January, February timeframe to have time to complete that online course. So if you are a high school student who would like to apply, you need a teacher to recommend you, you can go to the BWSI website for all of the information about all of the programs that we offer, because there's a whole bunch of them. I'm only involved in some of them. So I would recommend going to the website, and I will put that in. I don't know if there's I can put that in the Q&A or something.
Yeah.
Also in my presentation at the end.
Absolutely. Yeah. If you would mind adding it to the chat, I think that would be phenomenal.
Yeah, I will go ahead and put the link for that in the chat.
Perfect. Thank you. Thank you so much. My next question is for Daniel. I have a little bit of an advantage because I'm very familiar with the ThinSat program. Bob Twiggs was here at Morehead State for about 9 years prior to his retirement, and we watched the ThinSat program evolve from the concept and some early iterations, the pocket cubes to the ThinSat. So that was fascinating, and Bjarke was involved in that entire evolution too. So it was really pretty incredible. Incredible program, a four-year program. And I can imagine that the students that attend that entire curriculum are extraordinarily competitive in engineering programs. And so my question is, I don't know if the program's been implemented long enough for you to have this sort of data, but I'd be really curious on how many of your graduates pursue engineering degrees and how they fare, because I can just imagine they'd be extraordinary engineering students.
Yeah, so it's funny. So even the student that's sitting in my classroom now, a lot of the kids initially, so one of the things that's really special about Montgomery High School is we're a physics first school, but instead of kind of looking at physics first and more of like a math remediation way, we really look at it more as a foundational, make observations, right? And then come up with ways to explain those observations and, kind of using more of a reform teaching pedagogy with that. So as a result of that, one of the things that it really kind of allows students to be able to do is think about this idea of mission proposal in a similar way. And one of the brilliant things about Bjarke's XinaBox chips with X chips, and the entire kind of system that Bob Twiggs has really developed is that it gives students very tangible ways to start thinking about, okay, how is this data that I'm collecting potentially going to answer this bigger picture question? So I get a lot of students, actually, it's funny. One of the things that you say, Ray, is highly competitive, engineers kind of at the end of the program. At the beginning, they're not interested in engineering at all. And one of the things that's really interesting is to see that kind of transition. And I'm actually really lucky because, right, with the Mars Ingenuity launch, a lot of the students that I do get, especially the female ones, as 14, 15-year-olds, they're really interested in the biological sciences, right? So kind of seeing them switch over into this idea of like looking at astrobio and the idea that, hey, like I can collect this really singular piece of data, right? And then be able to kind of correlate it to see how it might answer this bigger picture question. So it's a lot of proof of concept type missions, and really kind of the big thing is being able to get the students to see it more of as a systems engineering perspective. So, you know, that competitiveness, right, it develops differently. Whereas in more of a traditional route, you might have something like a robotics team, right? And, you know, they go through the mechatronics process, right? And they're more so interested in like the rover aspect itself. And then the other portion of this is really actually, believe it or not, more so of the equity aspect. And Brenda Dingwall over at NASA has done a lot of research, and she's spoken a lot about that in particular as well. And so one of the things that's nice about looking at this in terms of a 4-year process is that within any given year, it's not so much about how much the students do complete, but it's more so giving them the opportunity, right? And saying, here are all these guidelines, right? So these are all the different, you know, phases, as Bob Twig's curriculum kind of lays out, that we want to be able to hit. And, you know, each year the expectation is that students can hit certain, you know, aspects, but if they take longer than that year, then they have the flexibility to do so, right? So it's not constrained to this singular academic year. And it turns out that usually kids, or students in general, they move much faster than the guidelines that we set for them. And as a result of that, right, that's really kind of how we can change over those external motivators to become these internal ones. And, you know, before I know it, I suddenly have a group of sophomore girls, right, that are looking at not just these nanosatellites, but starting to think more so of the integration into CubeSats, right? And how is it that they can go from maybe looking at singular sensors, right, to sensors that can collect data and give, you know, information about outside of the context of just engineering, right? So kind of being able to connect environmental sciences into it. One of the things that when I first arrived here at Montgomery that Bjarke was able to help us out with was development of an SO2 sensor, right? So being able to kind of use the XinaBox X chips that come standard as a launching off point. And in that way, right, really getting that internal motivators to turn in. And then suddenly, before you know it, right, in front of your eyes, they've turned into these really highly focused engineering students that, you know, care about a lot of those nuanced details, whereas in the beginning as 14, 15-year-olds, maybe not so much. So I think that's really one of the prime benefits of a curriculum like this.
Fantastic, phenomenal program. It's absolutely phenomenal. That's a good transition to the question I have for Bjarke. And of course, I've had the great pleasure of watching XinaBox evolve from the very beginning to this extraordinary system that it is now. And in your talk, you said something that was fascinating to me. You referred to it as an ecosystem with universities and high schools and the private sector, and not just in South Africa, but literally all around the world. And my question is, you know, it certainly takes the sort of ecosystem to do what you've done to launch as many XinaBox systems as you have, and to have to create those sort of opportunities for students worldwide. But my question is, how do you go about creating an entire ecosystem like that? And
I was on mute. So yeah, so how do you go about? Well, so first of all, you know, I only learned to spell satellites with the right number of L and T's and I's here when I met you, Ben, 5 years ago. Jude and I, who started the company, you know, we were helping a number of international business here with various things in South Africa. And one of the tasks we had was to try to develop engineers. Of course, there's many different ways of doing that. And we were being tasked to kind of like come up with a program where high school learners, students, got interested in STEM. And what we did, and Ben, that was when we met you back in 2015, I think it was, first time, was that we traveled around the world and ended up at in Moorhead with a solution there that we took around. And what we wanted to do was we wanted to, we bought a satellite from Interorbital back there in 2014. Haven't launched yet, but you know, one day. And what we wanted to do is that we wanted to come up with a technology where high school students could put a satellite together kind of like ambitious, because the other little requirement we had was that you shouldn't need a lab, you shouldn't need to solder, you should not need to have hardware knowledge. There was a lot of things we wanted to kind of eliminate. Now, being a software guy myself, I'm not, electronics. I've never been educated in electronics, and way less in satellites and satellite technology. So what I actually did was I built some things, a technology, so I myself could, put electronics together and build a satellite together, and then the only thing it will take was coding. And as we know, coding just requires a laptop. It's considerable less of a requirement for institutions wherever you are in the world if you just have to do the coding. So the technology, and it actually started, interesting enough, with a Pocket Cube, because I think one of the early Pocket Cube standards was it had a little 60-pin connector. And a 60-pin connector on a 5x5 centimeter satellite, I thought it was a little overwhelming, okay? Never mind the 104-pin you have in CubeSat. But I mean, this is a quarter of the space, and you still have 60-pin. So I wanted to come up with something that was didn't have all these pins. And I know it's like all single board computer. I mean, Raspberry Pi still have 40 pins and so on. I wanted something where you could just click it together. And that's where this thing has started. We kind of like came up with a standard, a protocol, a format. And I'm originally from Denmark, and so is Lego. So a lot of Lego inspiration. I mean, our module is actually built on the Lego standards of the sizes and the tolerances and things like that. And we started from that point of view to come up with this technology here. And yes, I got an opportunity at SmallSat to present it to Bob Twiggs, who said, cool, I'm going to take that and suggest that as the outreach program for the ThinSat program. And a lot of the schools that was involved in the early phase was, of course, all schools in mainly Virginia, because you guys was involved. It was also in Kentucky and I think Indiana. There was a couple of other states that had some schools involved. And a lot of the schools said, listen, we want to have some of that in the satellites. So we then, came up with a model where we could actually get the X-chips, as we call our modules, courtesy of Bob Twiggs, who gave it the name. We wanted to have a solution where we could put them into the ThinSats. And so it went. And that's actually how we kept on then developing this ecosystem, because we then came up with more and more sensors. And while it kind of like maybe sound and look impressive, having, I think we have like over 80 different modules today, it's not too complicated, because when we have to R&D a module, we only have to do one module that have to work isolated. We don't have to get like a motherboard up and running or anything like that. So we developed a number of different more modules. Especially we wanted to have something that was interesting in space. Whatever you want to measure on the ground here with like temperature and humidity and pressure and things like that is not necessarily the same stuff you want to measure once you send a ThinSat into space. So we kind of like then have to add on. We also decided that we didn't want to be a walled garden. We didn't want to isolate us from anybody else. We want to, everybody who had other stuff that want to play with it, we want to interface with that. So we did, bridges to Raspberry Pi, to BeagleBone, to even microbits, which is very popular in the UK and Europe. So we kind of like made sure that it could be used for a lot of different things. And as we normally say, you don't need a lab, we don't need a clean room, you don't need a solder station, you don't need an oscilloscope, and especially in a lot of schools that don't have the same opportunity that maybe a lot of American schools have, coming from South Africa. We have a lot of institutions where they have a computer lab, but they don't have a physics lab or electronics lab. And they maybe only have that when they get to university, and then it's too late. We need to engage high school students. You have been doing that, Ben. I know having your programs that you go out to schools and make sure you can recruit to more hits. Daniel, I think that, you got into this thing here from Mike Galvin and Princeton, trying to recruit your students. So Ben, you're not getting them from Daniel, I think. So so we kind of like needed to have this solution that the high schools could build this thing here and get excited about STEM and use space as an inspirator and not set too many to make too much of a stumbling block in order to build something and get a like out of box experience. And that was our goal. And I think that, Daniel Lee, I think you guys was one of the finalists in the seat in the Department of Education's CubeSat program last year. So you were one of the finalists. And it was that kind of programs that kind of like gives the option for high school students to actually eventually choose an engineering degree. Whether it's space engineering or biology or anything else STEM, is whatever they choose in the STEM field, that's a goal.
Yeah, absolutely. Well, it's been extraordinary to follow the development of that program. For Pauline, love the presentation on the CubeSat kit and the evolution of the different versions of it. But I have a little bit broader question for you. There was an image you showed of all of the students that are involved in the PolySat, and I assume the CubeSat kit program. And I think you mentioned that we're something like 80 to 100 students a year that you guys are working with. How on earth do you mentor on a hands-on applied engineering program? How is it possible to mentor that many students?
This is what we wonder every day. How do we do it every day? Well, first, it's not just me. I'm very fortunate to have 3 research engineers that are working as soft money engineers like here around. And so without their support, that's something that the program couldn't exist without. I'm a faculty, so my second job, which is according to the university, my first job is to teach, especially at Cal Poly. So yes, so we have that system of employees, like these engineers that work full time. And then we have divided the students. We have 2 lab managers, and then we have each pools having like kind of a pool is a subsystems, and then we have systems engineering too, and assembly and testing type of pools. And so they all have leads. So we try to have that hierarchy. And kind of going to one of the question about knowledge transfer, this is also how we are trying to ensure that knowledge is transferred when those leads can pass on before they graduate knowledge to the next lead and have that overlap so we don't lose too much. And documentation, but that's an everyday fight. I'm sure at high school level too, at university level too. So documentation is hard. I try to push that when I have graduate students to have that in their thesis. So they have to have that to graduate, but that's a difficult one.
Excellent. Well, I appreciate you guys have answered a number of the questions as we've been going along here in the chat room, but the questions are pouring in. So let me see if I can pick 1 or 2 here that you haven't responded to. This one is for Daniel from Amber. And as an educator, what motivated you to incorporate satellites into your curriculum? What was your motivational reason for that?
Yeah, so it's actually funny. Bjarke kind of briefly touched upon it. I originally started my teaching career down the street at Princeton High School, and this guy, Mike Galvin, reached out to me and was like, hey, there's this program and I need mentor schools. Are you interested? And I was like, I know nothing about satellites. This is totally new for me. But one of the big things for my graduating class coming out of my master's program for education was as physics teachers in particular, we were looking at this new set of science standards for the state of New Jersey. And even in the United States as a whole, with the next generation science standards, one of the core fundamental ideas is how is it that, the previous question about content transfer, right? How is it that we can get students to understand the concept that science you learn in physics is the same fundamental science that you learn in biology, right? Is the same fundamental science in chemistry, right? That process remains the same throughout all of these different content materials, right? But by changing the content material, right, students a lot of times feel like what they're doing is something completely different. And one of the big gaps to kind of bridge, in my opinion, was specifically that, not just in content and within our own department in science, but in the United States, you know, technology and science are split up. And no one really understands fully why. And, you know, we have these, you know, tech schools, and I'm sure Albert with the CTE talk is going to talk more about that as well. But we have these tech schools that really highly hyper-focus and specialize in that. And then, you know, in more of a public education setting, right, that isn't a magnet per se, right? There's more of this hyper-focus in terms of just the content of the science. And the integration between the two is really what we lose. So really what I saw was an opportunity, right? And not just that opportunity, but one of the things that Bob Twiggs, I think, was brilliant about is, you know, he made it very real by offering students this idea, you know, there's a real launch, right? Something you touched is gonna go to space. It'll be on the rocket, it'll go through, it'll be on the manifest, right? And I think that aspect of making it real, you know, when you're 16, 17 years old, right? Like it's a game changer, right? And in terms of in an educational context, right? When we talk about how do we make these external motivators become internal ones, right? An external motivator of a space launch it's a pretty good external motivator, if you ask me, right? And then through that process along the way, right, getting students to buy into that, you know, it is an iterative process, right? And you can answer these questions, right? We can attempt to answer these questions that you guys actually care about. And as a result of that, right, that's when those internal motivators of the space launch turn into more, or those external motivators of the space launch turn into those internal ones, right? So, and the ThinSats really lend themselves perfectly to that. And like my presentation went through, right, it doesn't just have to stop at ThinSats, right? We can look at nanosats as a whole, right? Scale up to CubeSats. And then, you know, by the time they get to college or university, right, they're hopefully able to, you know, compete with some of their peers in that aspect, you know, and have creative, you know, mission proposals while still being able to have the technical skills underneath to support that.
Mm-hmm. Absolutely. Excellent. This question's actually been answered for Rebecca, but Rebecca, if you don't mind, I'd like, for the benefit of every panelist and the audience, to have you expand on it a little bit. The question is related to funding and staffing of the program. And it looks like you have some fantastic corporate sponsorship, but how do you go about soliciting and maintaining that sort of sponsorship for this program, which it's so expansive. It must be an expensive program, and you know, it looks like you guys are expanding it. How do you maintain it? How do you solicit, maintain it, and grow it as you have?
Yeah, so there's a couple parts to that. I think I give the easy answer, which is we have industry sponsors. So we do try to keep the cost fairly low. A lot of the time that I put into it is volunteer time. I'm not actually paid for a lot of the development of the course. So my time only really gets paid for the 4 weeks when I'm directly teaching. There's obviously many other hours that go into it, as the other educators on this panel will understand, but I do that mostly volunteer time. We try to keep the actual cost of the hardware fairly low. It's about $250 per kit per student. And for some of the programs that we're looking on expanding the program, we're actually just going to give 1 kit per team, so that reduces the cost as well. We had to give a kit to every student for last year and this year because we're going virtual, so everyone's doing it independently in their home. In terms of soliciting funding and maintaining those relationships, I am very fortunate that I don't have to directly worry about that. We have an excellent director of the program, Bob Shin, who is very good at finding funding sources and making those connections and maintaining those relationships. So we are very fortunate as instructors that the funding is really just provided to us by our excellent director and the staff that works on Beaverworks as a whole.
Mm-hmm. Well, it's fantastic that they seem to understand the return on investment for the entire community and the entire industry ultimately. So that's fantastic. I'm going to combine a couple of questions because we're running a little bit short of time and the questions keep coming. And this is for any panelists that would like to contribute. What are your suggestions? And Rebecca's done this to some extent for converting such a hands-on type curriculum and course and laboratory sequence into online learning. And of course, that's related to the times we live in and just in general. You know, how do you, what recommendations or suggestions do you guys have?
I'll give it a, I think the beauty of CubeSat or ThinSat or the overall community in that small satellite community is that we are using commercial off the shelf. And so going back to Rebecca's point, and we've done that here also at CalPoly, is if they cannot come, then we need to send the kit or the part to them. So it might be easier if it's a software. It's a bit harder when you have a kit to handle to them. And also can become harder if it's a kit and you have to send it to foreign countries now, because now we have to deal with export control. But if they can buy, if it's more like of an open source and they can buy in their own country, that also can bring the cost down of what we want to teach. Like for example, for the kit, you could have it 3D printed. So if you have somewhere a 3D printer, you don't necessarily need to have a CNC machine to handle aluminum, and that bring the cost down. And then Arduinos or Raspberry Pi or whichever other type of electronics we have heard of are available. I want to say in most countries. I didn't do a study about that. So if someone wants to challenge me about that, that's fair. But it's somewhat available, and as long as there's the instruction then to assemble it. So I guess this is the other part of the learning aspect. If I don't give you the kit now, let's talk about assembly integration. You know, that could be transformed into a learning objective. So that I think that's one way that that hands-on based aspect could be provided. If we don't go to them, if they cannot come to us, then we need to bring it to them.
Absolutely, and it's an increasingly important, I think, these days. Anybody else? About Bjarke, you're all around the world, and
yeah. So you know, I mean, our technology was, of course, almost born for this thing here, because you know we wanted to make a technology where you don't need a lab. You just need a computer. So we actually have seen somewhat grow here during the pandemic, because we had a lot of interesting enough, a lot of universities who chose to use our technology. So one that kind of like stood out for us was that Stanford, who use our technology both on undergrad and a postgrad, because the student have to work from home. And you can't afford to have every student have a full lab at home. And, you know, as the pandemic just continues to move on, they only started the program here in January this year. I mean, you know, we started training the faculty last year, but they started only beginning of this year. As a result of that, hey, this is you know, going to go on for a while. And they're now on the second semester using our technology. And especially because the student can actually have it at home. I mean, we have like a standard CubeSat kit, which is both a ground station and you know, what you call a flight station, simulate a satellite, where all the different modules that you need in order to learn the concept of satellites is there. And of course, the student can then develop the software further. I mean, that's the easy part, because that you don't have to specifically have any equipment on and laptop to do the software. And then yeah, I agree with Pauline. You know, it's a matter of can you get it different places in the world. We use electronic distributors, which most of the universities are shopping at anyhow. So ours is you know, freely available around the world, and I also think that whether it's a Raspberry Pi or Arduino or those kind of things, you can get them most of the places in the world. So it's a matter of choosing a technology that don't require a lab, because that is the difficult if each student have to have that at home, and just have the space for that is many times a limitation for students as well.
Absolutely, excellent. This question comes from my colleague, Dr. Boris Yendler, who will fuss at me if I don't ask it, and it's for everybody. It's related to an issue that we all have with small satellites and CubeSats in particular, thermal management. Is thermal management part of the education or course curriculum? And I think there's an opportunity here, particularly when you're teaching physics and some of these underlying courses, to apply those laws of thermodynamics in a really interesting application in small sat thermal management systems. So for Dr. Yendler, could you please provide any insight into what you incorporated into thermal systems in the curriculum? Daniel, I know that you have physics courses, and I assume they touch on thermodynamics, but is there a link between the thermo and the space systems design?
Yeah, absolutely, right. So energy is, so for the student population as a whole, really energy is that constant theme that we kind of look at, right? So whether it's in a physics context, chemistry, or biology, it's specifically for space systems, right? We look at temperature in this idea. It could be as energy, right? If we look at it with IR, right, with an IR camera or an IR array. One of the things in terms of mission development that we always try to think about with thermodynamics, right? So a lot of like that TVAC testing, right? That's done more so on the actual Virginia space side. But what the students need to consider is this going to be something that we are looking at, as in terms of ambient temperature, right? So when we think of thermodynamics, right, is it specifically of an object or is it of the surrounding environment? And I think one of the things that I like to focus on is how do we determine what it is that we should care about? So again, kind of coming back to that mission proposal aspect with the physics. So not necessarily looking at thermodynamics in kind of the traditional physicsy sense, if you will, but more so in terms of specific application, right? What is it that we're trying to actually observe? What's the data we're trying to collect, right? And how is it that actually affects the physical then design of the actual hardware itself, right? So when we think about, here's a sensor, right, that's going to be inside of this thermally enclosed system, right? Is it smart to try to collect ambient temperature, right? Like, I think for a lot of us, it's a pretty obvious question, but for a 14-year-old, I think a lot of times it's difficult. They see temperature is temperature, right? And they don't necessarily think of it in the context of energy or in the context of particularly what it is that it's representing. So in that way, right, getting them to kind of solidify, right, and again, have that concrete connection back to the content material that they might be learning in the classroom, so that when they get to their sophomore or junior years and they start looking at these novel approaches, right, they have that concrete information that they can kind of rely back to and move forward from.
Absolutely fabulous. As I hear about these programs, I really wish they had been available when I was in pre-college and college. Unfortunately, we're out of time. Where did it go so quickly? And there are tons of questions left. So for the audience, I would recommend that you go back to the presentations, and I believe that you could find contact information from the presenters on those presentation recordings. So please, if you would, don't forget these great questions, and if you would, please forward them directly to the presenters. I expect this group would be very happy to provide responses. So unfortunately, we'll have to end it there, and I'm going to turn it back over to David.
All right, thank you, Ben.
And thanks all the panelists.
Definitely,
Thank you guys. It was awesome.
So, and that's the conclusion of the Educational Programs Live Q&A panel. So thank you everyone for joining, and a special thank you to Ben for moderating, and all the wonderful panelists that we had today for the Educational Programs panel. So thank you again, and be sure to stick around for the next panel and the rest of the exhibits later.
Thank you, Ben.
Thank you so much,
Thank you,
guys.
everybody.
Thank you.
Thanks, Daniel.